Owen, it's all yours.
Thank you very much. Can you hear me? Yes, good. The afternoon slot, sometimes difficult for both you and for me, and there's free beer waiting afterwards. So do try and stay with me. My name is Owen Woods, and I'm going to talk about sustainable or green software. Climate change is one of the most urgent and serious problems facing humanity. Right now, geopolitical factors are gaining a lot of attention. But if you just think about it for more than a moment, if we get the climate wrong, the geopolitical factors will get worse and worse and worse. So we have to sort the climate out. And you're all thinking, absolutely, I'm limiting my flights, I took the train here, I do my recycling. And that's laudable, well done, continue to do it. But I keep meeting people in the software industry who are convinced that software doesn't produce any emissions and therefore has nothing to do with climate change. I'm afraid, immediately after lunch, before the beer, I've got some bad news for you. Yes, we do. And actually, we're quite big indirect emitters. As any climate scientist will tell you, measuring anything to do with climate is really quite difficult. It tends to be approximations and models and estimates, but that doesn't mean it's wrong. It just means being very precise is difficult. If you look at the academic studies, and they look at our industry and call it ICT, so Information and Communications Technologies, they all estimate that we produce between 2 and 4% of global emissions, which doesn't sound much until you realize that aviation, one of the bad guys, produce 3%. That means we're actually in the naughty corner, on the naughty step. We're actually worse than aviation. I'll also just scare you a little bit more. The aviation industry, along with the motor industry, extraction, and many others, are working very, very hard and very quickly on reducing their emissions. What do you think the software industry is currently doing about its emissions? We're increasing them, and not subtly, really quite dramatically. So you can see actually what's going to happen is the graphs are going to cross. And actually, the software industry, the ICT industry, is going to it could end up being one of the biggest emitters. As I say on the slide, it's growing at least partly due to AI. One estimate that I didn't actually find it, a colleague found it in another talk, but data centers could use 5% of electricity by 2030. How much electricity does Germany use as a percentage? About 3%? 2.5% by some estimates? That's just the data centers. So that's not mobile devices, it's not your computers, it's just the data centers. The data centers are the most optimized part of the entire industry, and they could use 5% of global power. And Microsoft's greenhouse gas emissions, we'll come back to Microsoft, they're not really bad guys, but because they owned up to it, their greenhouse gas emissions last year went up by 30%, mainly due to AI, but that's quite a frightening statistic because they're big. I'm not going to take you through the studies. Frankly, they're not that interesting unless you're very into climate science or statistics. But you'll spot where the graphs are going. This is from what they call a meta-study. So somebody did a literature search, pulled out lots of studies about the ICT industry, and compared them. And actually, it's a fascinating paper if you like meta-studies. Otherwise, just look at where the graphs are going. From our perspective, they're all going the wrong way. So it almost doesn't matter what the scales are. They're all plotted on the same scales. We have a problem. So who am I and why am I talking to you about what appears to be climate science? Actually, I've finished talking about climate science now. I'm now going to talk about software, I'm sure to your relief. My name is Owen Woods. I work for a company called Endava, about 12,000 people globally. I'm the chief engineer, which is a hugely privileged position. I'm the top of the technical career tree, very lucky to be there. Prior to that, I spent about 10 years building products, which many of you I know do, and then about 10 years building software in capital markets, or as I like to say it, moving money around in infeasibly complicated ways. The reason this is a topic I'm interested in is I did a part-time PhD actually it took nearly 10 years, but that PhD started off in describing software architectures and then pivoted into energy efficiency. And the reason I was very interested in energy efficiency was because of its direct impact on climate. So I've been looking at this area for quite a while, and finally the industry's got to the point where it will accept cranks like me coming to conferences to talk about emissions and software. So we'll quickly talk about some fundamentals. That's really just checking we've all got the same language. And then the question is, what should we do? It's not much point wringing our hands. We need to know what to do. And I've got some practical architectural principles and tactics that you can take back to the office tomorrow or whenever you're going back, Monday. This is the conference that's got the AI theme. And I've already mentioned AI is not the best thing for software emissions. So we'll talk a bit about how AI relates to emissions, and maybe even what we could do about it. And then I've got a practical case study. We do some of this work out in Dava, and I've got an example of what one of our teams did to reduce the emissions of a machine learning pipeline. They did fantastic work. I'd like to celebrate that with you. And then finally, I'll make some suggestions about what you could do when you go back to the office to get cracking and help solve this problem. So green software fundamentals. The first thing is a bit of terminology. I hate this term. Everyone talks about carbon. It's a very bad rap for an element that has nothing to do with this problem. This is nothing to do with carbon. This is to do with a gas called carbon dioxide. Only for some reason we can't say carbon dioxide, so we all say carbon, which is a bit confusing. The other thing that's a bit confusing is there are many greenhouse gases, as I'm sure you know. Carbon dioxide is the largest by volume, and one of the least dangerous, actually, by toxicity. So, but everyone talks in terms of CO2 equivalent. So, and that gets shortened even by climate scientists to carbon. So that's why we say carbon. I prefer to say greenhouse gas. But you'll find me saying carbon right through this talk because everyone uses it. There's two sorts of emissions. There's two sorts of greenhouse gas emissions that we are responsible for in our industry. The first one are embodied emissions. Those are the emissions that occur, normally completely outside our direct control, when people make stuff. And there's three real areas. One is supply chain. What do you make a data center out of? What's the stuff that you make a data center out of? Yeah, probably not bricks, actually. That's the problem. Concrete. And how is concrete's environmental footprint? Yeah, pretty bad. So supply chain, people make concrete to pour to make data centers, for example. They make steel to make racks and to make servers and so on. Then there's actual construction, pouring concrete, putting things together. That industry creates quite a lot of emissions as well. And then there's hardware manufacture. And we'll actually talk a little bit about hardware emissions in a minute. But the hardware manufacturing process clearly creates emissions as well. So these are all the things that happen before we ever think about a piece of software. It's creating the data center and the hardware and the consumer devices, etc. The other bit of the emissions is what we probably feel we have more control over, are operational emissions. Those are emissions that occur when we actually run our software. And they almost entirely come from energy. That's electricity. And as you'll know, electricity can be generated in very many ways. Some ways of generating electricity have a very low emissions footprint, such as wind, and some have a very high emissions footprint, such as burning coal. And most, as we'll see in a minute, most grids are a mix of the two, which is why I've got both arrows going in, because it's pretty rare to find data centers that entirely run on clean energy. So that's, excuse me, that's why we need to be worried about emissions. We directly influence or drive both embodied emissions and operational emissions. And we need to be aware of both as we develop our software. Looking at embodied emissions, it's quite important to think about what kind of device you've got. The scale on the left-hand side is percentage, not absolute. Your consumer devices have very low operational emissions. They sit idle a lot of the time. They don't use that much power. They've been optimized not to use power. Nothing to do with emissions, everything to do with battery life, because people compete on that. But of course, there's a lot of embodied emissions in creating an iPhone. So most of the emissions in a mobile device are embodied, and a little bit is operational. A server, on the other hand, is right the opposite end. Firstly, server manufacturers, partly because of European Union legislation, are now quite sensitive about the embodied emissions of their kit, and they've been reducing it. But also, these things are on the whole time, burning power. Even if you're even if it's a 2% CPU, it's still using a lot of power. And many servers are not really optimized to reduce their power. They're optimized to maximize throughput, although some are specifically optimized for power. So when you're thinking about embodied emissions, you've got to think about what devices are involved in my system, because your system includes all the client devices as well as all the server devices. The operational emissions, as I said, they're all about electricity fundamentally. What we talk about is the greenhouse gas intensity of the energy you're using, and then the amount of energy that you're using. And the amount of energy is, what's your demand? So that is, how much work am I trying to get done? And then how efficiently is that done? And some of that efficiency is in our control, and some of that efficiency is in the data center operator's control. You may have heard of PUE, which is a data center efficiency coefficient, which is used in lots of the models. That's largely outside our control. The graphic on the right-hand side comes from electricitymaps.com. I snapped it on the 6th of September. The browner, those are European countries, obviously. The browner, the higher the greenhouse gas intensity. The greener, the lower the greenhouse gas intensity. So it's not a huge surprise that in Northern Europe, where there's a lot of hydro and a lot of renewables, on this day it was all pretty good. And there's one country in particular, you could probably work it out, I won't name and shame it, but you can figure out who it is, uses a lot of coal. And that's fundamentally the infrastructure they've got today. And they haven't got any hydro, and they haven't got a lot of wind either. So one country in particular is much, much denser. And then if you go right down south into the Balkans, there's an awful lot. I mention this because and the other thing is this is a snapshot at a single minute in time. The greenhouse gas intensity of your grid can change all the time. And I would say all of your countries will publish that data in real time via an API. And there's probably an app, such as Electricity Maps' own app, that you can actually go and find out more about that if you don't know about it already. The one that, when I give this talk, sometimes people put their hand up and say, how about France? Because they look at it suspiciously and go, that's very green. How do you think France pulled that off on the 6th of September? Nuclear, yeah. I had a German lady in the last talk who was really quite offended by that. If you're offended by that, it's just the way it's measured, I'm sorry. We're just measuring emissions, not potential downstream problems with nuclear. And I completely accept that limitation. So what can we do then? We like a good principle, don't we? There might be some principles we could follow to make us more greenhouse gas emission aware. Hopefully there'll be some architectural tactics, or design patterns maybe, and there might even be some tools we could use. Luckily there are. Let's consider principles and tactics today, because I've only got another 30 minutes roughly, I think. The Green Software Foundation is a vendor-independent organization of vendors, really, both services and software product vendors, who are very interested in reducing the greenhouse gas emissions of the software industry. They're a member organization. I'll leave you to go and find out about them. I'll talk about them briefly at the end. But they've come up with 6 principles which are very useful to bear in mind. The first one is sort of obvious, but emit the least amount of carbon, greenhouse gases possible. Yes, that's obvious, but actually, unless you start from that as a principle, nothing else really makes sense. Then if you reduce your energy consumption, then you're very likely to reduce your emissions, which is where the second principle comes from. And the third principle goes back to that map we saw, and the fact that electricity grids vary in their emissions density at different times. So think about moving your workload to times when your local grid is producing as few emissions as possible. That's often overnight, by the way, as a hint, which is somewhat counterintuitive, but it quite often is. Then think about all of that hardware, and for that matter, all those data centers. How do we reduce our embodied emissions, our embodied carbon? And then we need to know how we're doing. So we need to measure, even if it's imperfect, because even an imperfect measure allows us to see the trend. Remember the graph at the beginning? All of those are imperfect measures, but they're all going the wrong direction. So for our systems, can we get the graphs going in the other direction? And the last one is quite subtle, really. They're hinting at something. understand the exact mechanism of carbon reduction. Has anyone got any ideas to what they're hinting at there? Because not all reported reductions in emissions are actually reductions in emissions. Doesn't that sound strange? What do some companies do rather than actually reduce their emissions? Yep. They buy financial instruments, such as credits, to allow them to state that their emissions are lower than they really are. That's particularly something to watch on cloud vendor dashboards. I'll come back to that later, but that's what they mean. They don't want to say it too explicitly because it's quite unpopular with some large organizations that might fund them. What they mean is don't let people away with buying carbon credits. They need to reduce their emissions rather than pay to pollute. There's a few more principles I'll just go over quite quickly. The first three came from my PhD work, and they are link your emissions to your business transactions. It's very hard to get business people directly interested unless they realize they are the problem. We don't create software for ourselves, generally. We run software to perform business transactions. So business people need to understand the emissions that they're directly responsible for. Second thing is, it's easy to try and do local optimization with this stuff. I was having a conversation with somebody earlier about potentially optimizing your programming language. That's nearly always the wrong place to start. If you think about it as a system-level concern, like a quality attribute, that forces you to think about it for the system as a whole and make sure you're not locally optimizing, you're optimizing for the whole. And the third one I found was that emissions need a cross-functional team, a bit like DevOps. You're not going to get a smooth path to production and really good operation without having dev and ops people work together. And to reduce your emissions, it's not going to work unless you have the application people, the infrastructure people, and the business people in the room. Because you need all three views of it and all three sets of people to prioritize it. A few other just pragmatic things based on what I've noticed people doing. Actually focus on high-impact changes. I know that sounds obvious, but actually people quite often look for something they can do that's interesting or quick and easy, and they feel they're making progress. And often those changes don't actually produce a big impact. Second thing is don't ignore your non-technology emissions, my favorite being flights, but commuting is another one. They can produce very significant emissions. They're probably counted by some other part of your firm, but what I've seen in organizations repeatedly is they're counted by another group who never feed back the fact that you should be reducing them. People just tell them how many flights they've done, and there's never a feedback loop. So we need to build that in ourselves and challenge ourselves. What other emissions are we creating outside our technology? And finally, understand the importance of the software emissions in your overall organizational emissions. If you're Google, your software emissions are a big deal. That's because you're a hyperscaler software company. If you're a deep water logistics firm and your core business is moving container ships around the world burning heavy fuel oil, I'm guessing that your software emissions in your data centers are probably not the biggest thing to fix first. If you're in one of those firms, go and talk to the business people about their emissions. There's nearly always something the software teams can do to help, if nothing else, creating data for them so they can actually see what their parameters are to reduce their emissions. So moving on to kind of practical stuff, there's a couple of sort of classic tactics which have been used repeatedly by people trying to improve their emissions for software systems. The first one is called demand shifting, and I hinted at it earlier. We often have quite a lot of flexibility over where and when we do the processing. Machine learning jobs being a classic example, but also end-of-day runs and reporting and calculations and risk and all of those things can often be moved both in time during the 24-hour period, but also in location. Have you ever looked at your cloud provider's regions and the emissions density of each? They all now publish them. Sometimes you have to go digging for it, but they now all publish them. Different, because the grid is different in different places at different times, you will find that the emissions that your software is creating in a region vary depending where you are. So if you can move your workload into times of day where your local grid is producing less emissions, or you can move workload to locations where the emissions are lower, just do it. You don't even really have to measure. You just know this is going to be better because you can see there's a percentage difference. So no matter how much you're doing, you're just going to be that percentage better. So it's a thing you can just go and do. It's never really going to go wrong. Of course, there are trade-offs. And of course, it depends. This can add a fair bit of complexity to your system. We've done a bit of this, demand shifting of machine learning workloads between cloud regions. It was more complicated than we thought. It actually requires quite a lot of software mechanism to do it. Also make sure that you're aware of all the emissions. The classic mistake I've seen teams make is they say, it's currently very green over there, let's move all the data over there, which will take 2 hours to transfer, and then run the workload, and we'll save 8%. Well, that only makes sense if moving the data doesn't cost just as much in emissions as that 8%. And it can be quite difficult to know if that's true or not. And the final thing is, make sure you don't accidentally drive cloud vendor behavior. This is something Adrian Cockcroft has written a good blog on if you search for it. Don't trigger huge amounts of demand in regions where you don't expect to use it in the long term, because if a lot of people do it, what will the cloud vendor do? They'll build another data center. Think of the embodied emissions in that. So if you're big enough, you should be having that conversation with the cloud vendor about where you want to run your workload to minimize emissions. A second tactic is called demand shaping. It sounds similar, but it is actually different in how we think about it. It's much more about varying the demand rather than moving a fixed demand to other places. Demand shaping is about saying, there are options in our system. The classic one being in web apps, the quality of graphics that we download to the end user device. You also might be able to, for example, statistical processing at certain times. It might be acceptable to sample a data set, and at other times of the day or the week, you might need to process the whole data set, which would be massively more compute intensive. Demand shaping is about hunting out those opportunities to reduce the demand for workload, meaning you're going to do less, meaning you're going to consume less energy, and probably less compute, reducing both your operational emissions, but possibly your embodied emissions too. So this is actually real grid carbon intensity from the UK, which I'm sure it's on the slide somewhere when I snapped it, I don't remember, but it's fairly recent. So you can see there's significant savings to be made at certain times a day. So if we do, for example, if this is statistical processing, we do full statistical processing when the grid is fairly green. Then we do, as the grid ramps up at the start of the day and becomes quite dirty, we just start doing sampling. And then during the day, we have to do full service because that's what the users demand. And then again, when it's really bad at the end of the working day, we tell users we're going back to sampling because it's only 1/10 of the workload, and then we ramp it back up overnight. What's the obvious problem with this? One, complexity. You could create effectively a very complicated system. The other problem is, how often do you go to your users and say, we are going to decide how accurate your calculations are? That's not normally a conversation that ends well. That's normally no you won't, we're paying the bills. We just like the calculations all the time. I've seen actually relatively few situations in an enterprise application where this was actually possible. Where it is possible is often in web apps, where, as I said, it's things like how much do you download to the browsers, and it may actually be less about demand shaping in time and simply making the web app more efficient. And the Green Web Foundation have got a lot of advice about that on their website. The third tactic seems a bit counterintuitive, really, but it's all back to that. Do you remember that embodied carbon chart? The fact that operational emissions on clients tend to be very low. And I have a real example of this, except that I haven't got time to do it in this talk, because I've only got time for one case study. But a large auction house did this some years ago and reduced their both embodied and operational emissions quite significantly. The reason is desktops and mobile devices are idle for most of their working lives. Their CPU tends to be very low on average, and actually they often aren't using their memory either. Yet, those devices are still using roughly the same amount of power, And they certainly, all of the embodied emissions are in them. You can't change that. So effectively, you have almost net zero emissions if you can move workload onto the client, and if that workload displaces server workload, you've got a net positive. You will reduce your emissions. So for example, can you pass raw results to a client for processing? Again, there's an it depends, isn't it? That's quite interesting. Are you going to generate lots of emissions from the data transfer? But if you're not, perhaps you can do some of the heavyweight processing on the client. Remember, these client devices are now very powerful. Can you cache data on the client to stop it having to be stored in server memory? And actually, the one that the auction house did is, can you avoid a lot of resilient back end by moving a smart resilience mechanism to the client, which is more common today anyway. And the trade-offs are, once again, you've got to watch adding a lot of complexity to your system. You've got to be very sure that this is really going to have a positive effect. The other thing is, you become very dependent on the client devices. There's two possible problems there. One, that's lots of testing, because you've got to test across all the families. If you put lots of load on client devices, what are end users more likely to do? Change their client devices more often. How much embodied carbon is in a client device? Quite a lot. So actually, it's quite a subtle trade-off, this one. You don't want to force people to upgrade their devices more quickly, because that produces lots of embodied emissions. But on the other hand, if you can move workload to clients, that can help a lot. My fourth tactic is simply to measure stuff. That's to get an idea of what are the emissions we produce at different times, how do our emissions change according to the different workloads we run, and how are our emissions different in different places. As I said earlier, it all tends to be quite difficult to be very accurate about, but it doesn't really matter. An approximation is a good starting point, and climate scientists deal with approximations all of the time. Good place to start is your cloud vendor dashboard. They do provide some assistance, but beware. The emissions they show you may be different. Remember Principle 6, understand how emissions reduction is achieved? This is what they're talking about. GCP shows you location-based data. That's actually the emissions produced, or their estimate of your emissions in a particular place at a particular time. AWS, and last time I checked, Azure as well, they adjust your emissions according to the carbon credits that they've bought. So if they buy more carbon credits, your emissions go down. No, they don't. No, it's just an excuse. Your emissions are where they were. They've just made them look better. So ask hard questions of your solution architects. Make sure you sit your solution architect down in front of the dashboard and say, can you explain this? Hint, the answer is always no. Can you find me someone who can explain it? Yes, we can find someone. When that person arrives, say, could you just explain where the data comes from, how you do the calculation, and by the way, do you include market mechanisms or not? Because if a lot of people ask that question, they'll make changes to it. If nobody asks, they won't. You know the way it works. There are also third-party people like What Time and Climatique. They have free tiers. You can get started for free, but they effectively sell you reliable and well-understood sources of data so that you can do estimations of emissions. And other tactics, there's lots of them. I just kind of throw a few up, really. I need to keep moving. Throw a few up. But the key thing is really try to do less, because when you do less, you are almost certainly creating less emissions and saving money. What's not to love? Look at AI very quickly. As you know, AI-based systems require huge amounts of computing resources. So to absolutely no one's surprise, they're a sustainability horror show. And that's why Microsoft's emissions grew 30% last year, which is quite a frightening statistic. I hope it doesn't continue on that trajectory, particularly as Microsoft actually take their emissions quite seriously and absolutely know the problem, but it's not clear right now how to solve it. The key determinants, if you've got control over this, which I realize if you call through an API you may not, but if you're doing your own AI as model size, the amount of time you spend training and the amount of inference, that's the query step that you do with the models, all of that produces emissions. If you're doing data science, you may have come across the CRISP, the industry standard model for machine learning. This is their SDLC for machine learning models. Some things we need to think about are, when they're doing what we would call business analysis, start thinking about emissions as a quality attribute. Don't start thinking about it later on. Start getting product people to think about, are they happy with their emissions footprint? If they are, that's fine. They're making the decisions. But let's get them thinking about it as a system quality. For data preparation, could we use existing data sets? How do we minimize the amount of computational and other work we need to do? Can you minimize the amount you store, for example? This is a common problem in machine learning systems. A massive amount of data is stored just in case. Could you get rid of it? Because all that storage requires electricity. When you're modeling, could you not? Could you use a pre-trained model and then use RAG or fine-tuning perhaps? Can you shrink the models, quantization, so that they're much more efficient they use less memory and they're more efficient to query? Can you demand shift the training and evaluation so that you're doing it at times and in places with low emissions or lower emissions? When you're running your evaluations of the model, can you work out if you could use a smaller model so that it will be more efficient right through its life cycle, not just through training? When you deploy a model, can you run it in a region, not move it to the region, but always deploy it to the region, which is, for example, backed by hydroelectric power? That would be a fantastic step forwards. Can you use specialized hardware that minimizes energy usage? That's very, very rarely something people talk about with GPUs. We need to start talking about it urgently. What is the energy footprint of the GPU, not just how fast it runs? And then when they talk about monitoring and maintenance, they're only talking about how well the model is working. Well, that's important, but we've also got to monitor what its emissions are right through the life cycle. And when we're talking about optimization, don't just optimize the model, optimize our emissions. So to give you an example of the kind of work you can do, this was done by a normal team at Indava who wanted to reduce emissions in a machine learning environment. I say we, the team did the work, not me, I'm just telling you about it. So as you know, machine learning workloads are a bit of a sustainability nightmare. The team wanted to minimize the footprint they had. They were classifying Japanese handwritten characters. It was a 10-minute execution time in the pipeline, but they needed to do it many, many times a day. So it wasn't like a one-shot. It was something they had to be able to do a lot of. So they thought, this is worth working on. Having read that they'd done their green software certification and they'd understood their tactics, they said, what we need to do is move this in time if we can, or in location if at all possible, so that we can minimize the emissions. This is the team. So my colleagues, I'm lucky enough to have at Indava, they're all from Serbia. Anyone from Serbia? They're all from some of our Serbian delivery units, apart from Usman and James, who are based with me in London. They're two of our design authorities, so industry-specific architects. The team started by doing some measurement. Remember, if you don't measure it, you don't know if you're getting better. And they said, well, they ran it at 8 o'clock for some reason, I've no idea why, in the Western European region of an unnamed cloud vendor. And they found estimated emissions of 125 grams of CO2 equivalent, which is not a huge amount, but remember, this will run many times for a long time. This was the idea. And they then looked around the other regions they could run in, and they found they could save about 25% of those emissions by moving right then. And also, when they looked at round the clock, they found that it was also possible to save sometimes up to another 15% by moving it around the clock, by delaying the workload, in effect. So that would be a 40% saving. That would be huge. If every machine learning pipeline in the world could save 40%, that would be a really material improvement. So it's worth exploring. So they had a machine learning pipeline. This was running on Azure, I think. Yes, I'm sure it was Azure. And it had a temporal scheduler, and you could also trigger things manually, say, I want to run batches now. The first thing they did was it started off running in a single region. So they figured out how to containerize it and allow them to move it swiftly, as in single command really, from one cloud region to another. That's obviously the mechanism. That doesn't save anything itself, but that's the mechanism. And then the real green software bit was they needed to work out, both in future-looking estimates, but also in real runtime estimates, what would the emissions for this pipeline be? And the way they did it was, we used electricity maps. They were the people, do you remember the colored maps earlier? It's the same people using their API. Rather than binding to it directly, which is quite complicated, the GSF have got a carbon-aware SDK. So that's a software development kit. It's a library, think of it a bit like Spring, which allows you to do a number of things related to reducing your carbon footprint, a key one being retrieving data more easily than having to interface to all the different providers. So they used that to interface to electricity maps, and they wrote an Azure function which could be triggered to get the data, perform the calculations, and then store electricity metrics in a database so that they could also do estimation based on historical metrics. So that gave them theoretical greenhouse gas emissions per, I guess it was kilowatt hour of power. The bit that actually measured it for real, we used a thing called the Green Metrics tool, which is a piece of open source. That puts a little harness around your software. It then uses, they've got lots and lots of effectively internal plugins for different platforms, and they estimate your resource usage for a particular piece of work on a particular machine at a particular time. They do that in real time, dump that in a database, and then they've got a dashboard where they can take input from your electricity grid carbon intensity metrics and then tell you what your carbon intensity would be for that piece of workload. It's a very nice, very useful piece of kit. You're not expected to read this and understand it. It's just to say, it turned out not to be a trivial job. This is a sort of pseudo BPML kind of description of the logic, which one of the BAs did, is that it turned out to be a bit harder than they thought, which is partly why you'll notice, oh, I didn't think of the build, it's not a small team, and took them a number of weeks. This was thought to begin with to be, how hard can this be? The GSF talk about it all the time. Went, oh, actually, turns out it's reasonably hard, because there's quite a lot to think about. I mean, key things in it are, there's two decisions have to be made. Is there a region that is materially better than the current region we're defaulted to move the workload to? Yes or no? And then, could we delay the workload? And the business rule was just as simple as simple. It's, if a human being asked for this now, no, we can't. We have to proceed and use whatever region we can now. If a human being didn't ask for it, and so it was a temporal trigger, yes, we can delay it by a configurable amount. And they obviously have to do an estimate as to, will that make any difference if we wait 90 minutes or whatever the configured amount was? You clearly could do something even more complicated than that, but that was the sort of basic logic just to prove that this was possible and useful. And then finally, this doesn't render so well on these particular screens, sorry. This is the Green Metrics tool, and this is giving some insight into the energy usage of the software, the different runs of the software, and it can provide you with comparisons over time, so that if you're making changes or things in the workload change, you can tell what the impact is on your electricity consumption. So what they achieved, or was they achieved, not me, they did automatic demand shifting across time and space, and they kept a manual bypass so that if something was urgent, it could still be run. It's near real-time data, which is used for the decision-making, and that comes from third-party sources. There's no magic here. Those are APIs that you can go home tomorrow and access. And they used open-source software, the Green Metrics tool, to do the measurement, it's an estimation really, not a measurement, of the electricity usage of the actual workload. And so putting those two together allowed them to estimate what their environmental impact was and make decisions about whether they should demand shift or not, and whether it's time or space or both. So, supposing I've inspired you to take some interest in green software, when you get back to the office, what will you do? Any thoughts? I have a few thoughts. The first thing is learn more. I've been doing this stuff for some years, as you saw, and still every week I discover something I didn't understand about climate science, green software, electricity, data centers, or the intersection of all these topics. The good news is, back like 2017, 18, 16, actually there wasn't much information on this that was really consumable by software practitioners. It was mainly PhD students in software, to be perfectly honest, digging into many sorts of sources. Thanks to a number of organizations, which I will show you in a moment, their logos, there is now a lot of easily digestible information. In particular, there is a Linux Foundation free of charge training course on green software. You can all go and do it. It takes about 2 hours to do it, and you get a certification. And it goes over all of that basic terminology I was talking about and gives you pointers to other things. But today there are also books, and there's training courses, and so on. The first thing to start is do less. Use less hardware, use less energy. You don't even really need to measure anything. If you're doing less, you will be producing less emissions. So if, for example, an obvious one, don't commission lots of test virtual hardware that you don't need in your cloud vendor. One, you save money, and two, you will be reducing your emissions. Two, at the other end, you could be looking at your own system and thinking, we keep a tremendous amount of data. Do we ever use it? And perhaps the answer is yes, and it's important, and you have to keep it. Or perhaps the answer is never, and perhaps you could throw a lot of it away. Apple recently did a social media campaign called Throw Nothing Away. And a GSF ambassador from UBS picked it up and posted it back on social media going, do you see what we're up against? Even Apple are saying, throw nothing away. And I think Apple responded quite quickly, I guess pulled the campaign. But it was really interesting. Apple takes sustainability very seriously, on the one hand. There's another bit of Apple saying, don't throw anything away. We'll just let our disk space grow forever, which clearly is not going to help their sustainability. So it's about building awareness that just using less energy, using less hardware, is the fundamental thing that we're trying to do. Then use clean energy. That's a kind of macro level thing. Your operational emissions are your energy. If you can use clean energy and use less energy, then you will be reducing your emissions. You don't need to think about complicated system changes and difficult conversations with users about reducing their service levels. Just find a way to supply your machines with sustainable energy. Then you get into the stuff that we as software practitioners would be very interested in. And this start at the macro level. Don't start with the local optimization. Think about, there are quite a few patterns. I mean, demand shifting is one of them. But if you go to the GSF website as an example, or the Green Web Foundation, and there are others, they've got catalogues of things that you can consider doing. The big thing you've always got to remember is, what does Neil Ford always say? It depends. A lot of the tactics have got quite significant trade-offs. And not all the tactics make their trade-offs obvious. I'm also, some of you will know, quite deeply into security. And one of the tactics is terminate your SSL at your organizational boundary. Well, at this point, the security engineer in me went, no, don't even think about doing that. End-to-end security, that's the principle. So, nothing is for free. So you do need to think about them with a bit of nuance, but there's a lot of tactics you can think about, and for some of your systems, some of those tactics will fit straight in and might have a big impact. Finally, once you've done all of that and you're highly optimized already, think about code optimization. Are there languages you can use that are more efficient? Can you optimize algorithms and memory usage? Can you optimize storage usage? The reason I always say do this one last is twofold, really. It tends to be very high impact in terms of cost and time. Let's be honest, if you're in PHP, rewriting it in Go is not a trivial concern, is it? It's going to take a long time and a lot of effort that perhaps could be spent on other things. The other thing is actually the return on investment of this is not always clear. You really do need to do a lot of measurement and a lot of modeling to be sure that all the effort of doing optimization, code-level optimization, is actually going to pay off, and it often doesn't. If your system is, for example, idle a lot of the time and uses PHP, rewriting it in Go is probably going to make no difference at all because it's idle most of the time. If, on the other hand, you're a very high-intensity compute system, and there's definitely in scientific computing, there's a lot of opportunity here. They've got large and very inefficient codes, as they call them, that process massive data sets. they've probably got huge opportunities at the code optimization level. So again, it depends. To learn a bit more, there are now finally some books, and these are actually very new. I'd say the best known is Anne Curry, Sarah Sue, and Sarah Bergman's book, Building Green Software. It's very aligned with the Green Software Foundation. All three of them are involved with the GSF. Anne is a brilliant writer, and the other two are also great writers, but also great technologists. It gives you a very good overview of the whole area without it being a huge book. It gives you lots of things to go and think about doing. The second book's a bit more idiosyncratic. It's a self-published one. I only discovered it recently while doing a literature search. What I really like about it is that the advice in it is good. It's much, much less broad brushstroke. It doesn't give you lots of introductions. It gives you 6 chapters of 6 things you should do. And all the 6 things are probably sensible. I mean, keep your brain turned on, it depends, trade-offs, but all 6 are sensible. And although it is a little idiosyncratic, I liked it because it was very direct, very how-to, whereas Building Green Software, sometimes at the end of the chapter there's a it depends message, which you can't necessarily action. And then the Linux Foundation, the tiny URL at the bottom that's the Green Software for Practitioners course, which just go and do it. It takes you a couple of hours, you get a certification, and it covers all the stuff that I covered at the beginning in a bit more depth and rather more authoritatively than I can do it. And if you'd like to get involved, I think there's 4 organizations. The GSF themselves, you can't really get personally involved unless your organization joins, which can be quite expensive, but you can use all their resources. ClimateAction.tech is exactly the opposite, totally grassroots, no corporate membership, all organized on Slack, from the bottom to the top, so that's very accessible. SDI is the Digital Infrastructure Alliance. They're more about hardware and data centers, but they're very interested in moving into software. So if you wanted to get into an organization that's starting off, they're worth talking to. And the Green Web Foundation, very, very focused on hosting, developing and deploying web apps. And because of that, they've got some very focused advice, and many of us have got web apps. So it's only one bit of it, but they're very specialist in that. A few things to be aware of. On the left-hand side are data providers, all of which I think have a free tier. On the right-hand side, 2 standards to be aware of. If you want to calculate an approximation, but a calculation of the carbon, greenhouse gas, intensity of your application, the GSF have spent a lot of time and effort coming up with the SCI calculation, software carbon intensity. It's now an ISO standard, and it's freely available from their website. And that gives you an approach to starting to quantify your app. And the Tech Carbon standard is produced by a small UK company called Scott Logic, and for that reason, it doesn't get a lot of traction, but actually it's a different model. It seems to me to be very well thought out, and it's really interesting to read that after you've read the SCI, because it takes a slightly different approach to the whole problem, and Scott Logic are very into green software as well. I'm just about in time, so at that point I'll say thank you for staying awake. I realize after lunch that's not easy, but thank you for your attention.
Thank you. Thank you, Eoin. It was always a pleasure to have you here. We do have time for a couple of questions at least. Are you ready? I would ask him actually. Well, in any case, specific question regarding the tactic number 3, moving work to client devices. How would this reduce energy consumption when it increases energy usage for individual users? Every user device would consume energy separately instead of the task being done once on the server.
Yes, well in fact you find that the electricity usage on the client devices doesn't go up very much, because client devices, unless it's massively computationally intensive, you do need to do that calculation, I completely agree, but you find the client devices are using energy anyway, because the person's got the screen on, which uses a lot of the energy, and is using your app, so that using a bit more CPU in the app doesn't have a material effect, but because there's a lot of them all doing a bit of workload, that has a material effect on the amount of compute you need at the back end.
Thank you. Another question, probably the last one. How do you balance making software energy efficient while keeping it performant and scalable?
Great question. So yes, performance and scalability versus sustainability or green. It depends. It's a trade-off. It's a quality attribute. I think the key thing is that you surface it as a quality attribute, think about it as a quality attribute, and then that allows you to work with particularly product owners, but other stakeholders on what's the right trade-off for this system. Do we care more about our emissions or more about our performance, or is there a balance between the two that we need to make? Right now, because we're not thinking of them as quality attributes, it just tends not to get thought about at all. But when it comes to the trade-off, I can't really give you the answer, but it is definitely a trade-off, just as you all do every day on your systems with other quality attributes.
Thank you, Eoin. That's it for today. Thank you.
Thank you.
5 minutes break as always.